So we talked about molar mass, the mass of 1 mole. What do you think molar volume is? The volume of 1 mole. When we're talking about molar volume, we're talking about gases. Avogadro, his first name was Amadeo, by the way, Amadeo Avogadro. He did experiments involving gases, and he came up with an observation that's known as Avogadro's law. 2 gases containing equal numbers of molecules occupy equal volumes under similar conditions. This is something that's special about gases. This is not true of liquids and solids. But because gases have so much empty space, the size of the gas molecules really doesn't matter in terms of the overall volume. So if you have 2 balloons that have the same number of particles in them, they are going to be the same size.
Even though the atomic radiuses are different?
Even though the particles themselves are of different sizes. So, real life analogy. We've got a little elevator over here. I've been in it many times and stared at the thing on it, but I can't remember the maximum occupancy of it. But let's say it's 10 people. So you put 10 people in the elevator. Is it going to make a difference for your comfort whether you have 10 aerobics instructors or 10 O-linemen from the Fresno City College football team? It's going to be a little crowded with the O-linemen. It's not a big elevator. It's a small elevator. So the size of the person matters, right? Have you ever been to Wyoming? There's not a lot of people in Wyoming. The population of Fresno, without Clovis, is about 440,000 or so. The population of Wyoming is about 440,000. It's not a tiny state. At night, you can drive and drive and drive and not even see a farm light. It's just pitch black. It's beautiful, but there's just like nothing there, right? So, if all of the people in Idaho were aerobics instructors, size 0, or O-linemen, would it really matter given the amount of space that they have to occupy? No, it wouldn't. So liquids and solids are like people in the elevator. They're touchingly close. Gases, there's huge spaces between the particles. The size of the particle doesn't matter. It's a really weird thing about gases, but it enables us to do all kinds of cool experiments with gases. So if you have a mole of hydrogen and a mole of oxygen, they're going to occupy the same volume. And that does not make intuitive sense unless you realize that there's just an awful lot of empty space in a gas. I think we had the analogy of the soda cans. A can of soda, or was that a different? That was a different class, sorry. Yeah, scratch that. Rewind. Okay. The volume of a gas, though, is affected by the temperature and pressure of a gas. And so you've probably observed some phenomenon like that with balloons. So we do have to specify the temperature and pressure. And when you go on to Chem 1A, they'll get a lot more into this whole idea of gases. So we're just going to kind of touch on the surface of it. We're just going to look at molar volume of gases. But temperature and pressure are important. So we have standard temperature and pressure, abbreviated STP, which always makes me think of motor oil. Standard temperature is 0 degrees Celsius, and standard pressure is 1 atmosphere. 1 atmosphere is just normal air pressure at sea level. 0 degrees Celsius is the temperature of an ice water bath. It's the melting point, freezing point of water. So this is a very useful set of conditions because it's easy to duplicate. Most of these gas law experiments were done in like the 1700s. They didn't have electricity. They didn't know what atoms were, right? It was pretty primitive. But you can make something that's 1 atmosphere and 0 degrees Celsius without any technology at all. A container with a stopper and a piece of hose. Big vat of ice water. you can make a system that's at this temperature. So standard temperature and pressure, 0 degrees Celsius, 1 atmosphere. So it turns out the molar volume of any gas, the volume of 1 mole of any gas at STP is 22.4 liters. So this is another number that you need to remember. 1 mole of a gas is 22.4 liters at STP. And in this class, all the questions we're going to do will be at STP. Just so you have an idea, here's a regular-sized basketball and a drawing of a cube that's 22.4 liters. So, kind of sounds like a lot, but it's a little bigger than a basketball. So this table, it's kind of a silly table in a way, but it's still helpful. If we look at number of moles, here they've got different gases listed. 1 mole of each of these. How many particles in 1 mole? Well, because they're 1 mole, they all have Avogadro's number of particles. The molar masses, though, are different. But the volumes that they occupy at STP will be the same. So if you had 1 mole of hydrogen in a balloon, at STP, it would have a volume of 22.4 liters per mole. If you filled up another balloon with 1 mole of argon and it had 22.4 liters per mole, same volume, but would the mass of the balloon be the same? No. The mass of the gas will be different, but its volume will not. So let's calculate the volume of 13.6 moles of helium at STP. So we've got 13.6 moles, and we want volume. These questions really should specify the unit, but liter is a good unit of volume. And we need to divide by moles. They don't give you the conversion factor. You have to remember that it exists. The at STP is kind of a clue. Bless you. 22.4 is the number. Is it 22.4 liters or 22.4 moles? Liters. Is 1 mole. All of these things, molar volume, molar mass, it's all of 1 mole. Mass of 1 mole, volume of 1 mole. 13.6 times 22.4. 305 liters. Okay, how about this one? 25.0 milliliters of argon, and we want to know how many moles. Well, let's put units in here. Got moles. We know this relationship between liters and moles, right? What if we stuck liters down here? 22.4 liters per mole. Do milliliters and liters cancel out? No. So let's do this. Oops, that's not what I meant to do. That looked like absolutely nothing, didn't it? There it is. Let's move it over. It's magic. What do we need to stick in here?
1 milliliter over 1 liter.
Yeah. We need a conversion between milliliters and liters, but we need to be careful, right? So we want milliliters in the bottom rather than on the top so that the units work out. Sometimes you put them in wrong and then look to see if they cancel out, and then you realize, oh, wait a minute, I got it in backwards, and you can fix it. What does milli mean? 10 to the minus 3. It'll come back. My computer fell asleep on me. You guys are awake. I'm like, it can't stay awake. Um, 10 to the minus 3. Okay, we've had a lot of fun with my computer here. I'm not sure what the YouTube people are seeing, but my students are seeing the calculation, so we're just going to do it here. We have 25 milliliters, and then we need to multiply by 1 EE minus 3 to convert to liters, and divide by 22.4. And we're going to come up with a number of moles of 0.00112 moles, which might be better in scientific notation, 1.12 times 10 to the minus 3 moles. Any questions? Just don't ask me to do that again. Okay, we good? I think we're fine. Okay. Gas density. Gases are usually much less dense than liquids or solids. And so instead of using grams per milliliter or grams per cubic centimeter, for gases we use grams per liter so that the numbers end up being reasonable instead of being really, really small numbers. The mass of a gas, the density of a gas, uses the same equation as anything else. It's the mass divided by the volume. Here we're going to measure the mass in grams and the volume in liters. We can calculate the density of a gas at STP because we know the molar mass, we can figure out the molar mass of a gas, and we know the volume of 1 mole. So let's look at how we do that. Calculate the density of hydrogen sulfide gas, H2S, at STP. So these sorts of things are always fun because students go, oh wait a minute, and sometimes you lose your mind. Well, just take a step back and think about it. What is density? Mass over volume, right? Density equals mass, which would be grams, divided by volume, which would be liters. So we need to find the mass, and we need to find the volume. They didn't tell us how much gas, though, did they? The thing about density is it's the same whether you have a teaspoonful or a truckload full. It's an intrinsic property of the substance. So we can just choose how much gas we want to calculate the mass and volume of. A mole makes things really easy. So what we do is we choose 1 mole of gas. Can we calculate the mass of 1 mole? Yeah. Can we calculate or find, or do we know the volume of 1 mole at STP? Yes, we do. So the volume of 1 mole at STP is what? 22.4 liters. What is the mass of this gas? 1 mole of it. Yeah, we need to calculate it. 2 times 1.008 plus 32.07. So 34.086, right? That's the mass of 1 mole. So we calculated, we picked an amount of gas, we calculated the mass and the volume of it. And so I'm going to divide the molar mass by 22.4. Oops. And I'm going to come up with 1.52 grams per liter. Any questions? The hardest thing about a question like this is just remembering what to do. And sometimes in books they'll give you like a formula. Oh, well, the density is the molar mass divided by the molar volume of a gas. Well, that's fine if you're good at memorizing equations. What has always worked well for me is to be able to think about the problem. And that way you can do problems sometimes that you've never seen before. If you can think about, well, density, what is density? It's grams per liter. Any questions about that one? Here's another one. Boron trifluoride is a gas used in the manufacture of computer chips. All very nice. We didn't need to know that. Given that 1.505 grams of the gas occupies 497 milliliters at STP, what is the molar mass of boron trifluoride gas? Well, we have studied nomenclature, right? We could write the formula for this and calculate the molar mass. But what if we didn't know the formula? The information given here is enough to find the molar mass of the gas. So here again, let's think. What is molar mass? It's the mass in grams of 1 mole, right? Well, we have some information here. We have a mass and we have a volume. What if it wasn't 1 mole of gas? Could you still, if you knew the number of moles and you knew the mass, could you find the molar mass? Yeah, because really what we're doing is we're taking the mass of the substance and dividing it by the number of moles. So here we've got 1.505 grams. Well, that's convenient. They just gave us the mass right there. 1.505 grams of this gas. And here is a volume, 497 milliliters at STP. We're going to need that 22.4 number, aren't we? We can find the number of moles from the volume. So there we've got milliliters. We're going to need to get rid of those, because the 22.4 has liters. 1 mole of a gas at STP is 22.4 liters of gas. So if we convert milliliters to liters, then we can use this and we'll be fine. So 497 times 1 EE minus 3 divided by 22.4 says that this gas sample has 0.02219 moles. It only has 3 sig figs, but I'm going to add 1 extra one there so I don't have rounding errors. That's the number of moles. So I'm going to divide by moles. So I get 1.505 divided by 0.02219. And I'm going to get 67.8 grams per mole. Now boron is 10.91, and 3 fluorines, 3 times 19. So when I calculate it from the formula, I get 67.91 grams per mole. This is really close, isn't it? There are errors in any measurement, so we don't need to be disturbed that it's slightly different. Any questions?